thought we'd take a look at this problem for differential equations. I've been getting a lot of questions about it, and I thought I'd just do the problem. Let's see what happens. Okay, so we're given the rate of change of the temperature, we're given the derivative, and we're told that the ambient temperature, the temperature around the object, actually changes with time. And so we're given some values. We're given that K is zero point 0.2. Initially, we're told that the temperature is at 30 degrees Celsius, and then we're told that the ambient temperature is given by 20 e to the negative t. Okay, so what I would do is I'm just going to go ahead and substitute in what I know. So I'm going to call this t prime instead of dt, because that'll get a little confusing. And then I'm told that K is 0.2. And then I've got T minus, and then my ambient temperature is given by 20 times e to the negative t. Okay, now my first step is I'm going to go ahead and distribute that negative 0.2. And that gives me 4 e to the negative t. Now, I want to try to get it into our pattern that we know for using the integrating factor. So I'm going to move, and I forgot a prime there. I'm going to move this term to the left. So now that we have that, I want you to look at what we have. We have y prime plus p of x, or p of t, y equals q of t. Okay, that's the pattern we have here. When we have that, we identify P of t. So in this case, P of t is 0.2. And we can calculate our integrating factor by doing e to the integral of 0.2 dt. Now the integral of 0.2 dt would be 0.2 t. So we know that is our integrating factor. This is what we're going to multiply our equation by. So we're going to distribute an e to the 0.2 t. And so we'll distribute that to every term. Okay, now remember, the whole purpose of the integrating factor is that we recognize that this becomes the derivative of e to the 0.2 t times t. That is the derivative. And you have to think about it in reverse, right? So if you take the derivative of this using your product rule, you will get this expression. So we have that equal to 4 e to the negative t. Now we want to integrate both sides. So I'm going to integrate both sides. Now, when we take the integral of the derivative, of course, we get what's inside there. So e to the 0.2 t times t equals, and then the antiderivative here, oh friends, I did not multiply by e to the 0.2 t here. So let's fix that, because when we multiply, we add the exponents. That gives me negative 0.8 t. Okay, now we can do a u sub here. Do a u sub with negative 0.8 t du equals negative 0.8 dt. You can make the substitution there. We end up with a 4 over negative 0.8 e to the negative 0.8 t plus our constant of integration. Now, did a little maneuvering here. This actually becomes negative 5. So we have e to the 0.2 t times capital T equals negative 5 e to the negative 0.8 t plus c. Now at this point, I thought about getting t by itself. However, I don't want to divide my constant of integration by a variable. So what I'm going to do instead is I'm going to use my initial condition at this point to find out what C is, and then I'll divide by that e to the 0.2t. So I'm going to plug in 0. And don't forget, capital T is 30 when little t is 0. And we can solve for C. Okay, so e to the 0 gives me 1, so this is 30 equals e to the 0, so that's -5. We see that C becomes 35. Okay, so now let's go back to our equation and plug in 35 as our C. And now we'll go through and divide by e to the 0.2t. So we'll divide everything by e to the 0.2t. Okay, obviously here it's going to cancel out. We're given t. Here, we're going to subtract those exponents to give me e to the -t. And then this one I'm just going to bring to the top. So I hope that helps with this problem. This is what it was looking for capital T there. Let me know in the comments below if there's something else you'd like to see a video of. I'd be glad to help. Bye for now.